In this video, we'll add the gigabit Ethernet interface, using pin assignment to optimize the routability of our design, how to add signal integrity constraints from code, how to create topology constraints for channels that go through multiple components, and how to autorate high-speed interfaces, including differential pairs. Let's add Ethernet connectors from the library to this design. Connectors. All right, so here are RJ45 jacks. Copy this and we'll add it to our controller module. And we'll need 2 of them. Let's run that code. Referencing the docs, we can see the ports on that module, so this is an Ethernet connector wrapped with standard interfaces and pins for the LEDs. And it also has supports, which is what we're going to use to connect this device. Okay, so there's our 2 Ethernet connectors. We've previously used the net statement to make connections directly between the ports of components and modules. We're now going to introduce a more powerful mechanism, which is the require statement. We use it like this. Require ETH0, which is MDI 1000 base T from Ethernet jack 0. So this creates a port named ETH0 of type MDI 1000 base T. And you can connect to this like a normal port. All we need is that this Ethernet jack supports that interface in some way. So we can require another port from the other connector and then net them together. So we'll call that ETH1 and say net ETH0 ETH1. And what this will do is connect all the pins in an MD1000 base T bundle from one Ethernet connector to the other. Okay, so you can see that the entire media-dependent interface has been connected between the 2 jacks. One advantage of using requires is that you don't actually have to specify which pins the interface is on, you just get to connect to it. And another advantage is that using supports requires for making connections allows the router to swap connections. The legal swaps here are, if we turn on labels, we have pins A, B, and C. Let me flip this to the other side so we can see it right across. Just as before, we'll add some insertion points. So here I can route A to A. Pin-swappable connections have a purple rat's nest in the layout, and in the schematic, you can see that those purple connections are shown here as well in the net names. Press G. So things that have been routed are no longer purple. They exist like real nets. The rest of these could still swap, so they're left in with purple marks to designate that they can move around. Using Control A is helpful with pin-assigned routes. So if we select one of these differential pairs, press Control A, we see the valid targets for this design, showing that A and B can be swapped here. So we could select A to B and route. And then you can see using manual routing mode, again, those possible connections are highlighted. You can then route B to A. And as you delete these routes, you get the freedom back. Okay, let's clean up. We'll delete these insertion points, take this connector, and flip it back to the top side of the board. So far, we've been routing differential pairs using the default dimensions. To enforce good signal integrity, we want to use impedance-controlled geometry and make sure that all of the skew, loss, and topology constraints for this gigabit Ethernet interface are met. We add these constraints in 2 parts. One is a substrate model for the stackup, which translates electrical properties like impedance to geometric properties like a per layer width. And then the second part is the electrical constraints like skew and loss for the interface. For the substrate, helpers specifies a default substrate for us to get started with. This contains all the information you would want from a manufacturer for a fabrication drawing. So it has the stackup with specified materials, material properties, and dimensions. It has routing structures, which have per layer impedance-controlled geometry for single-ended and differential structures. And those models also have propagation and loss models as well for length matching and loss constraints. It also has the available via types for this design. We'll use this 100 ohm differential routing structure for the Ethernet routing. So that was a substrate model. Signal integrity constraints like skew, loss, and topology are applied with code, and code becomes a very simple way to manage highly complex constraints. So we saw that JSL, the standard library, has definitions for the common bundles like MDI. It also contains code that adds signal constraints to connections made with those bundles. So if we search the docs here, 1000 base T, can take a look at the constraint for this. Okay, and at the top we have some examples here. We've already got those set up. So let's copy paste this code into our design. And notice we've got a couple new lines here. We create a variable named MDI constraint and direct it to use a 100 ohm differential structure from our substrate. Then this toponet connects the MDI bundles and at the same time constrains the routing topology, which here is very, very simple, point to point. And finally, we apply the constrain function. And under the hood, this constrain function simply applies the skew and loss constraints from the standard interface. Instead of looking these requirements up and manually mapping the constraints to net names in every design, you just use the shared library to automate and standardize your practices. And of course, you can get in there and tweak those numbers if you want. Save and run this. Okay, and let's demonstrate our new structure here. So we add a routing point back in, and we'll have to flip it so that it connects. And select those two and route it. We can see that we get a new differential pair, but it doesn't have the default dimensions. It has our impedance-controlled structure with specific spacing and clearance from our routing rules. And this would auto-update. So if we were to change these routing rules, change the stackup, this would just update to match. So you don't need to think about missing a length and screwing up impedance control with a design change somewhere. Everything just updates for you. Constraints for this MDI interface have been added, so all the skew and loss constraints, and they're being tracked live. So if you open the issues panel, this issues panel shows the status of the unsatisfied signal constraints. Think of it as a live DRC report. For example, the skew is not being met in these pairs. If you click on a pair, you can see the relevant issue highlighted in green, and if you double click on the issue, it will jump you to the relevant spot. All the SI constraints track dynamically as the design is updated, so as I move this around, constraints that have already been met, like topology and loss, are already resolved and don't appear in the DRC to-do list. So let's add the application circuit for this Ethernet switch to our design. This, like the FTDI chip, is a highly configurable component, and this circuit contains passives and test points and bypass, power filters, and the clocking as well, and has many options for configuring the device, which will then flow into detailed choices for configuration passives, for example. And again, you just have to use this high-level interface instead of pulling things out of a datasheet. So let's add our Ethernet switch, and we'll connect up the pairs as before. So let me move this constraint up so we have all of our definitions. And then we have 2 Ethernet jacks. So in a for loop, 0 to 2, we'll require an Ethernet interface from the ith Ethernet jack. We'll also require the interface from the switch, which is in the documentation. Where's our supports? Yeah, there we go. We have our supports. Looks like we have 2 of them from there. But we'll just need 1. So we require SWMDI. We bring up the toponet. and connect the MDI interface from that bundle to ETH from this jack, and then similarly we'll constrain it. So this is just going to loop through twice and connect and constrain both of the interfaces on the Ethernet jacks. And if you had a 8-port switch, you just change this 2 to an 8 and it's all handled for you. Alright, so let's save that and run it from a clean terminal. And here's our circuitry for the Ethernet switch. Let's translate that there. Okay, and we can use our pin assignment rat's nest to sort of guide the placement of this device. And notice that they'll update as it tries to find better estimates for which pins could go where. Let's go ahead and complete the routing here. So we'll add insertion points. This one needs to be flipped back. And let's do the same thing over on the switch. So if we select these pins and press Control A, all of the possible targets for those pins are selected at the same time. And if I use Control Shift and drag a box, we intersect and press Shift I, we get the differential insertion points on all the pairs. And now we can see that we should be able to just go point to point. So if I open manual routing mode, I'll be able to see the viable pin swaps as I go along. And I'll be able to say, yeah, I can actually just flow these pairs through, which makes sense. You should have a pin assignment that makes it possible so you can route all the high-speed signals on one layer. But it is good to double check. And you can see that our constraints code is still active, our impedance-controlled dimensions are being applied, and all of the skew constraints and loss constraints are being tracked. So we can finish up that routing. Let's just select these. And 1, 2, 3, 4. Route with Q. That made some routing decisions I don't agree with, so I can delete those and go back in manual routing mode and have a better assignment. And note that while we were doing all those swaps, the schematic was automatically being updated with the detailed assignments for those ports. Okay, that looks pretty good. So we've now de-risked the high-speed routing. We know that everything can be done on one layer. And we can experiment with the connector placements. This looks fine to me. And yeah, we're looking in pretty good shape. We can check the issues pane for any showstoppers, and largely we're seeing just skew constraints on the diff pairs for our signal integrity issues. All very manageable. With the design de-risk, let's finalize the channel design for this interface. We don't actually want to go straight from the connector to the switch with no protection. We'll want to run through an ESD diode first. We want to keep the nice high-level connections in the code and all the swappable interfaces. So again, we'll use a library function for adding ESD instead of hard-coding nets to pins. So let's install the diode library. Here we go. We use diodes. Open our SLM file. Paste in diodes. And yeah, we want to use this create ESD diode pool. So copy the example code and paste it in. Done that. So reading these lines, we create something called ESD, which is an ESD pool, and we'll actually need 4 to cover all of our signals, and then we'll integrate the rest of this into the for loop. And to do that, we'll let's check our MDI docs. We're also going to need the more involved code from the MDI constraint function. So this lets us set up an overall constraint topology that goes from the switch through the ESD and to the connectors. And it also is going to split up the differential pairs that we can route through the diodes. So this is going to let us basically apply arbitrary constraint code to our high-speed interface. So instead of toponet and constrain here, okay, we don't need the diodes, we don't need the constraint, we already have that. We have this within. And here we're going from MDI to Ethernet with a constraint. We require the protected pairs from ESD. So we don't need that line, and we don't need that line. There we go. And then that makes the connection from the source down through the destination. Okay. That looks good. And that's about as complicated as signal integrity code gets, where you have a non-trivial topology constraint through multiple components, closed end-to-end with skew and loss constraints. Okay, so our old routes were invalid, and now we can have our ESD diodes in place. And notice that all of the connections that go to these diodes are also swappable. So we don't actually have to figure out which diode goes with which signal and then edit a schematic. We can rather position them in place and have our code that constrains the topology and the loss and skew just flow right through these diodes. So let's get our ground pair selected. Auto-viad. We'll route the through connections on all the chips, and then we will want to go through, start adding our insertion points as well. For the rest of this video, I'll pop out into the physical design UI. Okay, add our insertion points. And I'll just route these manually. There we go. Notice that sometimes when you route, the routes will change dimension as you assign the pins, and that's because it doesn't necessarily know what the rules will be before you actually have the circuit created. So that's like, if you use an FPGA pin as a clock, you'd have different routing rules for it, but you don't know which pin is a clock until you actually assign its function. So that's why you're seeing these dimension changes there. Let's open our issues panel to see where we're at. So our unsatisfied signal constraints are just the skew between the pairs. The router can resolve all these issues. We just have to give it some room to work using a length matching region. So a length matching region is bounded by control points on either side. So Shift Q to open routing mode, hold down 2, and click and drag to add 2 control points. Now you can select this segment and change it to length matching, and a handle appears, and you can increase the size of this handle to create a region. And when we add that width, the router is going to adjust the trace geometry to satisfy the signal constraints. The router is adding bumps to reduce the skew in the diff pair to hit the MDI target of 800 femtoseconds between the positive and negative side. These bumps are sized to avoid creating impedance discontinuities, and that style is required for everything above 8 GHz. And you can resize this region to match your own preferences in placement. So here I'll just move it close to the, and you can change the pose exactly using this configuration here. Notice that the bumps are dynamically sized. So it is going to be doing very precise compensation just using the solver instead of having to do it by hand. So if I add another region, let's make this one a bit longer. I'll resize that. So the entire set of constraints for Ethernet is being implemented. So right now the unresolved issues are the skew and the diff pairs, but there's also a looser constraint of, I think, several hundred nanoseconds difference in skew matching, and the router is managing both. That other constraint is trivially met right now because it's so large, but if I take this and make it much, much longer, you can see that macro scale length matching starts to get added to the diff pairs to make sure that that overall larger constraint is met as well. So if I make that extremely long, it won't have quite enough room, and we'll end up with additional length matching issues in our design. So we're off saying that this let is too long, and I must say that I agree. We'll finish up by adding length matching constraints for the remaining routes and adjusting control points and clearances to make geometry that we're happy with. And with that, the router has deskewed all of our differential pairs, and we have no remaining signal integrity issues. In the next video, we'll wrap up this design by adding the microcontroller, again using pin assignment, and a bit more signal integrity routing for the RMII bus.